Welcome back to Calculus 2 practice problems, where we are looking at using the comparison tests, that's plural because we have two tests, the limit comparison test and a direct comparison test, to determine the convergence or divergence of a series. So the general premise is that if we are given some series with some sequence a sub n, and it's so close, the a sub n sequence is so close to this b sub n sequence, maybe it's off by something, we'll look at it. But if we know that this series converges or diverges, we can determine if the series we are given converges or diverges by either comparing them directly or doing a limit comparison test. So basically, depending on these tests, let's just look at the limit comparison test. So like I said, we're given the infinite sum of that a sub n series, right? And we know the convergence of b sub n. If we take the limit as n approaches infinity of those two sequences divided, and we get a finite non-zero number. That's the rule. If we take that limit over the ratio of the two sequences, it must be non-zero and it must be a finite number, so it can't be infinity. Then a sub n is said to match the convergence or divergence of b sub n. So we'll look at here's an example. Right, this is what I mean. It's so close to 3 over 4n, right? If it wasn't for that plus 1. And we know what 3 over 4n does. Look 2 videos ago at the convergent geometric series. We know that 3 over 4 to the n is a convergent geometric series when we rewrite it like this, right? And this is so close to it. So what we can do is take the ratio of the function or the sequence we have over the sequence we know to converge, and because that sequence equals 1, which is a finite non-zero number, or because that ratio is 1, a sub n will match the b sub n. It will match the convergence of b sub n. So the limit test is pretty useful. We also have the direct comparison test, which is a bit more complicated. Basically, we have 4 cases. If we know what b sub n does, if b sub n converges and a sub n is less than b sub n, then a sub n must also converge. So let me illustrate what that looks like. B sub n converges, right, which means as n approaches infinity, a sub n is approaching, look back to the sequence video, but I mean b sub n is converging, which means it's approaching a finite number, right? And if a sub n is less than b sub n, it must also converge. If it's less than or equal to b sub n, it will converge. Basically, it cannot just cross b sub n and diverge out of nowhere. Diverge means to keep growing as n grows, right? So if b sub n converges and a sub n is less than b sub n, then a sub n will also converge, right? But there's another case. What if a sub n is greater than b sub n and b sub n converges? Does it also converge? Does it diverge like that? We don't know. So it's meaningless to compare it to something, to compare a sub n to a smaller convergent series. We can say the same thing with diverging. If we know that the similar b sub n series diverges like this, we want a sub n to be greater than it because it will also diverge in that case. We do not want a sub n to be less than b sub n because we don't know if it will then converge or also diverge, right? So in words, it looks like this. If b sub n diverges and a sub n is greater than b sub n, then a sub n will also diverge. Once again, it's meaningless if b sub n diverges like this and a sub n is less than b sub n because we don't know if it will diverge or converge. But if it is greater than b sub n, it will diverge as well. Kind of like a squeeze theorem kind of thing. So let's look at some examples. Determine the convergence or divergence of this one. Well, this 3 is messing us up because if that 3 wasn't there, we would have the series from n equals 0 to infinity of 4 to the n over 5 to the n, which is equal to 4/5 to to the n, going from 0 to infinity. So it's a check that it's going from 0. It's a check that the absolute value of r is less than 1. We have a convergent geometric series here. This series is a convergent geometric, right? So we should always just do the limit comparison test. It's a lot easier, but sometimes it won't work, like later in this video. So the limit comparison test says that the limit as n approaches infinity of a sub n over b sub n must equal L, a finite non-zero number. Does it matter if we do b sub n over a sub n though? It actually doesn't, because then we would just get 1 over L, which is still, it's still a finite non-zero number, right? So the ratio doesn't matter. It just matters if that ratio, the limit of that ratio will produce a finite non-zero number. So let's take the limit as n approaches infinity of a sub n over b sub n. Right, this was b sub n right here. And let's hope that we get a finite non-zero number. So basically we can break a lot of math rules here. Basically this plus 3 is not going to matter at infinity. An infinite distance away, that 3 is really doing nothing. Right? You can even see that when n is equal to even 3, we have 4 cubed over 5 cubed, which is 125, plus 3 over 4 cubed plus 5 cubed. So we have a 4 cubed over 5 cubed plus 3 over 4 cubed over 5 cubed, right? This is very close to 1. So imagine at infinity that plus 3 is doing virtually nothing. So you can see when we compare it like that, these just cancel each other and we get 1, which is a finite non-zero number. So a sub n, or the sum of a sub n, matches the convergence of b sub n. So it is said to converge through the limit comparison test. We'll also look at the direct comparison test, but let's determine the convergence or divergence of this series. So what can we say about sine squared n? Sine squared n. How about this? Let's do a divergence test first. We should always start with a divergence test. That's the easiest way to determine convergence or divergence. Sometimes it works. What is the limit as n approaches infinity of sine squared n over n to the 3 halves? Looks like we'll have, the top doesn't really do anything, right? It's just bounded between not -1 and 1, but since it's squared, 0 and 1. The top will just keep alternating between 0 and 1. But the bottom will approach infinity, which means the limit as it approaches infinity is 0. Okay. What do we say when the divergence test equals 0? It is inconclusive, right? That's probably why it's in the comparison test video. Right, so what do we do for the comparison test? Since that test was inconclusive, we got to find another way to prove convergence or divergence. Well, remember when I said that this was just bounded between 0 and 1? So how about this? Can we just compare this to the series from n equals 1 to infinity of 1 over n? Won't those graphs behave very similarly? Because, or won't they grow very similarly, especially at infinity? Yes. And what do we know about this one? This is a convergent p-series, where p is equal to 3 halves, which is greater than 1. So we have to prove the convergence of b sub n here, or the sum of b sub n. Now that we know that this series right here converges, let's compare it with a limit comparison test. We know that the L is equal to the limit as n approaches infinity. And let's see if that is equal to a finite non-zero number. right? We have sine squared n over n to the 3 halves over 1 over n to the 3 halves. Well, the n to the 3 halves cancel, so we're just left with a sine squared n. That is not a finite number, right? It keeps changing between 0 and 1. It keeps increasing to 1 and then decreasing back to 0. So it does not equal a finite non-zero number. So the limit comparison test is inconclusive as well. Well, we found something that's very, very similar to it. Can we prove convergence using the direct comparison test? So in order for this to be a favorable comparison, we know that b sub n converges, right? So do we want a sub n to be bigger than or less than it? We want this to be less than, we want a sub n to be less than b sub n, right? A sub n must be less than or equal to b sub n in order for this direct comparison to work. Because if a sub n here, this is b sub n, if a sub n all is forced to converge, if it's less, it's not just going to diverge like I was saying earlier. But if a sub n is bigger than b sub n, right, if this one is bigger than b sub n, then we can't determine whether it's going to converge or diverge. It's not squeezed, it's not pinched between b sub n and 0, right? So what we want is for this to be less than or equal to b sub n. Let's prove that. Is sine squared n over n to the 3 halves less than or equal to 1 over n to the 3 halves? Yes, because isn't this the biggest that sine squared n can be is 1, right? And the smallest it can be is 0. So as it alternates through different values of n, it will always be less than or equal to 1, right? So it's because a sub n is less than b sub n and b sub n converges, a sub n will converge as well. Match the convergence of b sub n. So that is how we use the direct comparison test. Like I said, it should be noted that if b sub n was actually less than a sub n, it would not have been a favorable comparison. It would have been meaningless. So we have to have a meaningful, favorable comparison. So let's look at this one right here. Prove with both comparison tests that the series converges. Okay, well, what could we compare this to? Could we compare this to, I'm going to say that at infinity, this n right here and this n are kind of going to cancel each other out. They're going to grow, like the n is going to cause it to grow, and the n in the denominator is going to cause it to shrink at the same rate. So we can kind of ignore these. They kind of cancel each other out at infinity when you take that limit. So let's just compare it directly to this. Well, that's almost a geometric series, right? What we want to see is this. So can we just decrease this by 1 and then add 1 to the end? Remember, we did that in a few videos ago. So go back and watch the infinite series video if you're confused about how to change the bounds. And we know that this converges, right? This is a convergent geometric series because why is it convergent? Well, after you do that algebra, you'll see that r is equal to 1/2, which is less than 1. So we know that b sub n here, this b sub n, is convergent. So remember, in order for it to be a meaningful comparison with the direct comparison test, and b sub n converges, we want a sub n to be less than or equal to b sub n. That's the requirement. So we'll look at it. Well, first of all, let's put them on the same playing field and rewrite this as n equals 0 to infinity of n plus 1 over n plus 2, 2 to the n, right? First, let's do the limit comparison test, though. Let's do the limit as n approaches infinity of a sub n over b sub n, right? N plus 1 over n plus 2, 2 to the n, over, remember we wrote b sub n as this one, b sub n, 1 over 2 to the n. So like I said, at infinity, these n's cancel each other out, and these ones will cancel each other. So we can kind of break some rules. But 1 is a finite non-zero number, so it will match. It won't converge, it will match the convergence or divergence of b sub n. Since b sub n converges, a sub n also converges by the limit comparison test. So this is a neat test. Now let's look at the direct comparison test. The direct comparison test, we know that b sub n converges like this, right? And like I said, we want a sub n to be less than b sub n. Is it? There's a few ways you could plug in the two functions into your calculator, honestly. You could say x. Well, you can't plug them in because then you'd have to sum them up in your calculator, so it wouldn't quite work. But we can see that this one right here is actually less because the denominator is bigger. This ratio right here is always a fraction less than 1. Like, for example, when n equals 4, you'll have 5 over 6. When n equals 7, you'll have 8 over 9. So it's always a fraction that's getting bigger and bigger and bigger and closer to 1, but it is less than 1, which means that all of this is less than all of this, right? Because of this term right here. So I keep drawing circles, but we can see that it is always less, and it gets closer and closer as n moves on, but it's still always less than or equal to b sub n. So it will converge with a direct comparison, right? So we proved with both tests that it converges. So the limit comparison test is honestly more useful in my opinion, but the direct comparison test can definitely be useful as well. So let's look at a final example, right? Direct comparison test. How else would you do this one? It kind of looks like something you can integrate, right? You could definitely integrate this. You could do if you had the integral from 1 to infinity, couldn't you add 2 here and then subtract 2? So you could have x plus 3 minus 2, x squared plus 3x plus 1, x squared plus 3x plus 1. And this will all become an easy u sub, right? Or not quite, because you'd have a 2 there. So we want this to be 3 halves, right? And then this, you could complete the square and do an arctangent, right? Yeah, no, let's not do that. This is why we want to have a toolbox of all of the different kind of tests. So for this one, what I see is as we approach infinity, all of this stuff really doesn't matter. All of this stuff really doesn't matter, right? We can break the rules in this section. So really we can compare this and kind of compare this to n over n squared. The other stuff doesn't really matter. What does n over n squared become? 1 over n. Do we know what this does? Remember, we want to know what b sub n does. That's the point of comparing it to b sub n. Well, yeah, this is a divergent harmonic series, right? First of all, it's a p series where p is equal to 1. And second of all, you can prove that it diverges with the integral test. We did both of those at the end of the last video. So we can compare it with that using 1, the limit test, the limit as n approaches infinity of a sub n over b sub n. And like I said, this stuff's not really going to matter. This is really not going to matter at infinity. N over n squared over 1 over n is just equal to 1, which is a finite non-zero number. So it will matches the divergence. In this case, since b sub n diverges, a sub n will also diverge. Matches the divergence of b sub n. That is, a sub n matches the divergence of b sub n. So a sub n diverges. How about a comparison test? So now we have the other case. B sub n is diverging, right? It's not approaching a certain number. So we want a sub n to be bigger, right? Because then it's forced to also diverge. It can't just converge and cross if it's always bigger than b sub n, right? But if it's less than, we don't know if it will diverge or converge. So maybe you're getting into the hang of it, but let's see. Let me put it into words. We want a sub n to be greater than or equal to b sub n. Is it? There's a few ways to do this. N plus 1 over n squared plus 3n plus 1. We want to be greater than or equal to, but we don't know yet, 1 over n. So one way I like to do it is look at 1 or 2. Let's look at what happens when we do 10 and then maybe 20. Let's look at 2 terms pretty far down the line. I mean, it's not infinity far down the line, right? But if we look at 10 terms in and then 20 terms in, we can probably determine if it's going to be greater than or equal to 1 over n. So obviously when n equals 10, we have 1/10 and 1/20th for that one. That one's easy. And like I said, we want this fraction to be easier. We want this one to be greater than. So when you plug in 10, you're going to get 11 over 131, right? Is 11 over 131 greater than or equal to 1/10? Well, 11 over 131, or how about this? 11 over 110 is equal to 110, right? 131 is bigger than 110, which means that the actual fraction is smaller. Or you can just plug into a calculator and see that it's hard to see with fractions, right? But plug this into a calculator, you're going to get 0.8. Plug this one into a calculator, you're going to get 0.1. How about n equals 20? Well, n plus 1, it's already not looking good, right? But plug in 20, you'll get 400 plus 60 plus 1, or 461. That also doesn't look good because 21 divided by 461 is equal to about 0.5. And 1 over 20 0.05. Oh, well, in that case it worked, except if I didn't round, I rounded wrong first of all, but if I didn't round it would have been that. And we can see that this is not greater than, and this one is not greater than. So basically, a sub n is not greater than or equal to b sub n. A sub n is less than b sub n for intuitively all terms, right? So we cannot use the direct comparison test. It is not a meaningful comparison. We already know that it diverges, though, from the limit tests, and we saw how much easier the limit test was to do, so I always suggest starting with the limit test, or the limit comparison test. But basically what happens is, even though a sub n is less than b sub n, we already proved its divergence, so it will diverge, but by the direct comparison test, we don't know if it will just converge. So the direct comparison test failed in this problem, but the limit comparison test, we proved that it converged. So that is how we use the limit comparison test and the direct comparison test to determine the convergence or divergence of infinite series.